Lesson 38 in the era of coronavirus, limits involving infinity. You have seen this, you have watched this video, you have watched this, you have seen this, you have worked those, you have tried this, and you have worked the questions in the worksheet, trying your best on your own before you sat down to watch me. So I want to hit a bunch of these. These are a little bit more straightforward than some of the stuff we have been doing, so I'd like to show them if possible. Just talk briefly about many of them. Could a function have infinitely many vertical asymptotes? Sure. You can think about the tangent graph. There are infinitely many vertical asymptotes. You just decide where what x values you want vertical asymptotes at, and boom, you can have as many as you like. But how many horizontal asymptotes are there? Are there infinitely many? No. Why? Because how do we find horizontal asymptotes? We find horizontal asymptotes by taking a limit as x approaches negative infinity. That's one of them. And we take the limit as x approaches positive infinity. That's another one. There are only two kinds of infinities. So there are at most two horizontal asymptotes. This is one, that's the other. If this is a number, if this is a number. And if those are different numbers, then you have at most two horizontal asymptotes. But there can only be two horizontal asymptotes because there are only two infinities to head toward. Speaking of infinity, this is one of those scenarios where x gets larger and larger. What do we do with this thing? Well, one of the things we can do is divide everybody by the highest power of x that we see. This goes to 0, this goes to 0, this goes to 0, the whole thing goes to 0. What happens here? We divide everybody by the highest power of x that we see. The highest power of x that we see is x to the 1. This is also x to the 1 if you think about square root of x squared. We divide everybody we see by x to the 1. But when we divide by x to the 1, that's the square root of x squared. Looking for an eraser, it won't matter. That's 1. So the numerator gets closer and closer to 1, the denominator gets closer and closer to 1, the answer gets closer and closer to 1. So that is the officially rigorous way we think about this. You have a calculator, you can graph this function, look at bigger and bigger values of x, see where this thing settles down. You have a calculator, you can graph this as a function of x. You can look at larger and larger x values, see where the thing settles down. I'm going to offer two possible graphs, one for here and one for here, just talking about why they are the way they are. G of 0 is 0, G of 1 is 2, G of negative 1 is negative 2, and then this piece. As x gets larger and larger in a negative direction, the function values approach negative 1. So we've got some horizontal asymptote at negative 1, and the function gets closer and closer to it. Then as x gets closer and closer to infinity, the function gets closer and closer to 1. So we have some horizontal asymptote at 1. And as x gets larger, the function gets closer and closer to it. What happens in the middle? This happens in the middle. This is going to bother some people because they were told when they were in high school that a function can never cross an asymptote. That's blatantly false. This function clearly does cross an asymptote. What the asymptote does is it describes the end behavior. As x gets larger and larger, the function gets closer and closer to the dotted line, but there's no rules about whether or not the function can touch the dotted line. Coming down here, h of 2 is 1, h of negative 1 is 0. As x gets larger and larger in a negative direction, the y values get closer and closer to 1. All right, that's my function. So that must mean that we're coming up like so. As x approaches 0 from the right-hand side, the limit is infinity. As x approaches 0 from the left-hand side, the limit is negative infinity. And as x gets larger and larger, the y values get closer and closer to 0. Y equals 0 is a horizontal asymptote. So the function looks something like this. There are plenty of ways to do it, but this is the canonical way to do it. I want to talk a little bit about how L'Hopital's rule works, because this is a scenario where as x gets larger and larger, this goes to infinity, this goes to infinity, so L'Hopital's rule applies. By L'Hopital's rule, this is the limit as x approaches infinity of, and then we can just take the derivative of the numerator and the derivative of the denominator and try again. Well, this still goes to infinity, this still goes to infinity, so it's still indeterminate, it's still infinity over infinity, and we try again. Well, derivative of the numerator, derivative of the denominator. Now that's looking really straightforward. That's 4/10, which reduces. Yes, but couldn't we have just compared those in the beginning? Sure, but I want to make sure that we know how to use L'Hopital's rule in a situation where the numerator and the denominator both go to infinity. Here's a situation where the numerator and the denominator both go to 0. And so again, by L'Hopital's rule, this is the limit as x approaches 0 of, and we take the derivative of the numerator and the derivative of the denominator, and we try again. The numerator now goes to 1, the denominator now goes to 1, and so we're good. L'Hopital's rule allows us to take limits by taking derivative of numerator, derivative of denominator, and trying again if the thing is indeterminate. This limit is also indeterminate. Values of for f and its first three derivatives are given in the table below. So we think about what happens as x approaches 2. Well, as x approaches 2, the numerator approaches 0, and the denominator also clearly approaches 0. So again, by L'Hopital's rule, this is the limit as x approaches 2 of derivative numerator, derivative denominator, and we try again. The denominator goes to 0. The numerator also goes to 0. So we try L'Hopital's rule again. Derivative of the numerator, derivative of the denominator. The numerator is a nice non-zero number now, and the denominator is 2, and it happens to be an answer choice. Sometimes there isn't a table. Sometimes we just run L'Hopital. That goes to 0. That goes to 0. So by L'Hopital's rule, we take the derivative of the numerator, careful chain rule here, derivative denominator, and we try again. We think that we're done because the numerator, well, that's 2e to the 0. That's 2 times 1. And the denominator, secant, is the reciprocal of cosine. Cosine of 0 is 1. Turn that upside down. And we got it. So you can see that in previous years, I have given some questions that are very conceptual, where there's nothing for you to crank out per se, except knowing what L'Hopital's rule does. And there are some questions that are very procedural, where I'm thinking that's a 0 over 0, derivative, derivative, and go. So those are things for you to be thinking about as we go forward. There are several kinds of ways that L'Hopital's rule pops up. I hope this is helpful to you as you study. Best wishes for an outstanding performance.